Hi, and welcome to COSI 4785-5785. My name is Jeffrey Van Balen, and I'll be your instructor for this course. My email is jvb@uwyo.edu, and this is the way that you'll do most of your communication with me throughout this course, since, as you probably know, this is an online course. So in this course, let me just first comment that we're not going to cover the entire text. The text, by the way, that is listed on the web page, so you can decide whether or not you want to buy it, but I would recommend it. It's a good book. It's one of the kinds of books that you want to just basically keep forever, as opposed to buy for this class and then sell when you're done. And if you go on and perhaps take another class in compilers at some point, that course might use this same text. But in this class, we're only going to use about the first 8 or 9 chapters of the book. And basically, what the general outline of the course is that we're going to start out by talking about some theory. You may have seen some of this theory before in one of the theory courses in the department. But the difference is that in this case, we're going to take that theory and apply it. So we'll do that first. Basically, there are 3 to 4 major sections of the course. You can see that in the modules page of the course outline. And so the beginning, the first part is about formal languages. And we'll work our way up in increasing complexity of formal languages till we get to the point where we have a language. We have the formal framework for creating a language that's expressive enough that we could actually, program a programming language or build a compiler for a programming language. As I said before, this is an online class, so all the lectures will be posted just like this one. Often the lectures will not be each segment that you listen to will not be a full class period. So often you'll be listening to multiple segments to actually make up a class period. So I'll be making reading assignments from the text, and I'll also be making them I'll be posting some things online on the web page that I'll also be referring to and assigning readings out of those things. So again, if you don't buy the text, that's your choice, but I highly recommend that you do. The course policies are available also on the YO Courses page. That's a breakdown of basically the overall structure of the class. So there's some stuff about not cheating, which please don't do that. I hate getting involved in being a policeman. And it gives you basically what each part of the course is worth in terms of programming assignments. And there's no final in this class. There's only a midterm, which is not a midterm, which doesn't come in the middle of the course, but comes more like 2/3 of the way through the course. So programming assignments, the first one is pretty easy, but after that they get pretty hard. The second one in particular is quite difficult. So the time that I give you to complete those assignments assumes that you start when the assignment is given. And of course, I know that no student in the history of the University of Wyoming has ever started when an assignment was given, but I highly recommend you start as soon as possible, because otherwise, with the more difficult assignments, you simply won't finish them. I promise you that. Late assignments will be accepted but penalized. That's covered in the policy statement. The programming language that we'll use in this class is Java, and we'll be discussing how it's used and its overall function in the course, in the projects in this course in detail as we go through the course. Okay, so let's get into a little bit, just a very general introduction of what are going to be the topics today. Well, not of today, but of the course. So again, it's a course on compilers. So what is a compiler? Well, it's a program that takes an input program in a source language and translates it into some other language called the target language. That target language might be executable. It might not be executable. An interpreter, you've probably heard that term too. It's different from a compiler because what it does is take the source language and it appears to execute it directly. Okay, so the compiler doesn't execute the program that the source language describes. It translates it into something different, whereas an interpreter executes the program. These days, most programming languages are some combination or some hybrid combination of both a compiler and an interpreter. For example, in Java, there's a compiler, and it compiles Java source code into bytecode, which is then executed by the JVM, and the JVM is an interpreter. There are other components that we'll discuss here and there in the course that are related to compilers, such as preprocessors, assemblers, linkers, loaders, and then also a very important part of all of this is runtime environment. So you might wonder why you should care about compilers. I've had students tell me on a number of occasions, well, I'm never going to write a compiler. Why do I need to know about this? Well, I'd have to say that in my, I have sort of two different careers. I've been a professor for a long time, and I've also done a lot of commercial stuff. Well, a lot, maybe a little, but I don't know how you want to measure that. But nevertheless, in the commercial work that I've done, I have to say that the techniques that I've learned about compilers or in the compiler theory and practice have been more relevant to my work at more times than any other thing that I learned in my computer science education. The techniques for parsing and translation are used in, here's a list of a number of places. It's certainly not an all-inclusive list. It just scratches the surface of the possible applications of this kind of technology. So for example, translating Java comments into HTML, we use these techniques. To generate various outputs in table form from the results of a SQL query, we can use these techniques. Collating responses from email surveys, once again, we can use these techniques. Implementing a server that responds to a network protocol like HTTP or IMAP, can use this. Screen scraping, another thing that's not so much in vogue now, but for a long time was pretty hot stuff, where you basically write a program that reads data off of web pages. Now it's not so popular anymore to do this because most services that present you data on a web page also have XML type outputs, so you can access them and get the data in XML, and in which case you wouldn't have to use screen scraping. But nevertheless, the same techniques are usable to parse XML files. Another place this is used that you might not be aware unless you have some EE background is that hardware engineers use a compiler to translate hardware description languages into the schematics of circuits. Another place I've seen it used is in spam filters. So you write, what does a spam filter do? It scans your list of emails and parses them out and tries to find places in emails where spam is present, and that can use these kinds of techniques as well. Another reason that you should care about this is because it may be, maybe not, but it may be one of the largest software systems that you build as an undergraduate, the compiler that you will build in this class. And so, it's important to have experience and be able to tell potential employers that you've had experience building a large software system. If all the software that you've ever written is confined to 10 to 50 line programs like you generally work on in courses like 1030 and 2030, then that's not really very useful from a prospective employer's point of view. They want to see that you've had experience building a real system of some size. Another thing that maybe isn't of interest to you, but maybe it will become of interest to you as you see it unfold in this course, is that this area is one of the areas of big success areas in computer science. By that I mean a bunch of theory was done, And then that theory actually came to life. It was actually used, and people developed ways to use the theory to build real systems. And you don't see that too much in computer science. So that's kind of an interesting case study, if you will. Then you'll learn about programming languages a little more. It's, you'll learn a little of the same kind of stuff that you would learn in a programming languages course, but in more detail. How programming languages work, what are the trade-offs that you make in language design, things like that. All those things will come up as we go along. So this is a slide that you'll see a lot as this course goes on. It gives you the general structure of a modern compiler. You start with the source code there on the left, and it moves along through various phases until out at the bottom pops, maybe not machine code, but the target code, whatever it is. And we'll go through each one of these steps. They don't necessarily logically occur in sequence like this, but it's useful to think about them that way, and that is the way that we will approach them in this class. So we have lexical analysis will be the first topic that we discuss. And then we'll talk about syntax analysis, semantic analysis, intermediate representation generation, and then optimization of that, code generation, and then optimization of that. So a compiler is basically structured into an analysis part where the program is read in and various kinds of analyses are done on the source code. You can think of this as kind of a front-end processing. This begins with lexical analysis, where the program's divided up into lexemes. And then from those lexemes, something called tokens are produced. And then the next step is to do syntactic analysis, which is also known as parsing. So here we take the output of the last phase, the tokens, and we try to extract the grammatical structure of the program from that. We have to do that because, when you look at a program up in some editor, you can kind of see the structure by looking at it, but the computer doesn't have that luxury, right? So really, all the computer sees is a string, to begin with, is a sequence of characters. That is your program, right? So basically, this first part of the analysis is to recover that higher level structure that you see when you look at the screen. So that's what these two first steps, including the syntactic analysis, are about. And so the result of this is typically a tree, which we'll talk about these syntax trees quite a bit, and the tree gives you the structure of the program that has been recovered by this analysis process. This is also where, if the program is not syntactically correct, that gets caught during this analysis. Then we've recovered this structure, and now we need to find out if the input is meaningful. And we need to check various things about the structure that we've recovered. So if there are rules like you can't use a variable before it's declared, we check that sort of thing at this point. And then type checking is sort of a more general form of the example I just gave. Type coercion might get done at this point. So in other words, if you have an assignment of an integer to a real, you might, in whatever language you're using, you might be able to just make such an assignment. But in fact, what has to happen is some kind of coercion or conversion has to happen, and so that might be inserted at this point by the analysis code. Usually what happens as a result of semantic analysis is that some kind of intermediate code gets generated first. And the reason for that is it's easier generally to do various things with intermediate code than it would be certainly with the original input or with the syntax tree that gets generated. And so intermediate code, we'll talk about intermediate code and what kinds of features it ought to have. It should be easy to produce. It should be easy for us to write code to reason about it, and it should also be easy to translate it into the final target language that we intend to translate it into. Intermediate code is usually designed so that it lends itself for optimization and for semantic analysis. Code optimization may be skipped. Many systems, many compilers don't do it. We may do a little of it in our compiler for this class, but not a lot. But in general, it's a very important step where, if you're generating code for a particular kind of machine, for example, a pipelined architecture or something like that, then it might be very important to optimize code, to rearrange the generated code so that it takes advantage of registers or in certain ways, things like that. So that's a very important and also active research area of compilers. Optimization can be by far and above the most difficult part of the compilation process. Finally, we get to code generation, where we take the intermediate representation and convert it to the target code. A symbol table is an important element of this this part of the analysis. Actually, symbol tables are used all over the place. We'll talk in detail about what symbol tables are. You'll be developing your own in the projects in this class. So look for that to come soon, right after we talk about the lexical analysis, and you'll see how symbol tables are used. The compilation process may also be done in multiple phases. Generally, modern compilers do that. They generate code in multiple passes. Okay, so for next time, that's all for today, but for next time, read Chapter 1 from the book, and online you'll find, on the webpage you'll find a document called The Anatomy of a Compiler, so read that as well. Do the review questions for Chapter 1 as you go along. And if you have questions, well, obviously you can't bring them to class, but you can email them to me, or you can discuss them with your classmates, however you want to handle that. Okay, so that's all for today. See you next time.